We've been talking about trying to determine whether or not a series of numbers converges. So if we had some list of numbers A0, A1, A2, A3, A4, and then we start adding them up sequentially, will this infinite list of numbers eventually converge to something? Will it be a physical value? We've talked about the method of partial sums, which is we work out A0, then A0 plus A1, then A0 plus A2, A1 plus A2, A0, A1, A2, A3. We add them up, we find a formula for that, and we take the limit. And that doesn't usually work, though, because it's too hard to find a formula for the partial sums. In the previous topic, we talked about several tests. For example, the divergence test, which says that if the limit of the actual terms an themselves don't converge to 0, then the series must diverge. This is an easy to apply test, just involves us taking limits, but it doesn't work all that often. It's fairly inconclusive. We also had an integral test. Now the integral test essentially said that the series of an converged if and only if a related improper integral converges, where the sum, say, goes from 0 to infinity, the integral goes from 0 to infinity, and this function f of x was equal to a continuous underlying function. Underlying function meant it just had a finite number of bends, and continuous meant that we could apply the fundamental theorem of calculus. So this is a great test because it's never inconclusive, but you can only apply it when you have a continuous underlying function, and not every series, or not every sequence does that. For example, sequences who have -1 to the n, we saw in the sequence section, don't have underlying functions. Fortunately, we had another test called the alternator test to handle that case, and it essentially said that a summation of the form -1 to the n bn converges if and only if the limit of the bn sequence converged to 0, on the proviso that bn has an underlying function. So once again, this test is never inconclusive. But just like the integral test, you have to have some kind of an underlying function, for at least part of it. This is a great collection of tests, but none of them together would be able to tell me anything about this particular series right here, the summation n going from 1 to infinity of, say, 2n plus 3 times 6 to the n over n plus 1 factorial. Because if I attempted to look at the terms themselves, I would have the an's equal 2n plus 3 times 6 to the n over n plus 1 factorial. The minute I try to turn this into an underlying function, 2x plus 3 is fine. That's just a linear function. 6 to the x is fine. That's just an exponential. But x plus 1 factorial suddenly falls apart, because this is only defined for integers. I mean, plugged in x equals 1, I know what it means, but if you plugged in x equals 1/2, what's 3/2 factorial mean? Or plugged in pi, what's pi plus 1 factorial mean? The factorial function is only defined for integers, so it turns out that this thing is discontinuous pretty much everywhere you look. It's just a sequence of values. So there are some sequences who are quite literally only sequences who don't have underlying functions. Today I want to provide you with one last test who could handle this case, and then to show you how we can tie everything back to the radius of convergence question. The ratio test says the following. Given a series of the form summation an, compute the limit of the ratio of consecutive terms, an plus 1 divided by an, and call that limit r. If the value of r is less than 1, then the summation of an, the series, converges. If the absolute value of r is greater than 1, then the summation an diverges. And if the absolute value of r is equal to plus or minus 1, then this test is inconclusive. So before we put this into play, I'd like to give you at least some reason for why this test works the way it does. And it all has to do with this line right here. Imagine for a second that you know that this sequential limit is true. So that would mean that an plus 1 divided by an is a really, really good approximation of r. So that would say when n is really, really big, say 100 over 101 over a100 would be about r. And a102 divided by a101 would be about r. And a103 divided by a102 would be about r. But this first line says that a101 would be about r times a1. Oops, that should have been 100. Sorry. Times a100. This second line says that a102 would have been about r times a101. But the line above says that a101 is about r times a100. So that means that this is actually approximately r squared times a100. The third line says that a103 is approximately r times a102. But we've just seen what a102 is. It's approximately r squared a100. So if I plug that in here, then this is going to simplify to r cubed times a100. Now if I keep this up, what I'm going to see is that this formula right here means that all of the terms that are past 100 are going to look approximately like r to the n times a100. That means that the series an eventually starts looking like r to the n times some fixed constant. If I pull that constant out of everything, then we're talking about something that looks like an r plus an r squared plus an r cubed plus an r. And that guy right there is the geometric series. And we know that the geometric series is guaranteed to converge, provide the absolute value of r is less than 1. And that's exactly the first line. The other lines follow from the same idea. If r is greater than 1, then we know we're outside the radius of convergence for the geometric series. And so we have divergence. This last line, we know that the geometric series converges at plus or minus 1. But remember that this argument was all about being approximately equal to r. We have an approximate value, so I'm not quite sure whether I'm a little bit above it or a little bit below it. And that's kind of the heart of the inconclusive bit, which could be a little bit below it, which might mean you converge. You could be a little bit above it, which might mean you diverge. So the best I can do is say, this test would be inconclusive there, and it's a good thing we have 3 other backups to help out. As we're going to see in the examples, the ratio test is particularly effective when you've got a series that has at least one of the 2 following things. Either it's got a geometric term, r raised to the nth power, or it's got some kind of a factorial term in it. And we'll see that with series that have either one of these 2 pieces, the ratio test is fairly effective. So let's try some examples. Let's determine if the series n going from 1 to infinity, 2 times 3 to the n over 5 to the n plus 1 converges. Now you might remember we did this 2 topics ago using the Taylor series idea, but now I want to show you how the ratio test would work. So in the ratio test, we want to compute this value r, who's called the limit, as n goes to infinity, of a sub n plus 1 over a sub n. So I just got to figure out what goes in here. Now a sub n, well that's just the terms that we're adding. So in this problem, a sub n is equal to 2 times 3 to the n over 5 to the n plus 1. On the other hand, what's this a sub n piece? Well, it's not this. It's not a sub n plus 1. We don't just take 2 times 3 to the n over 5 to the n plus 1 and add 1 to it. That's not what it means. Remember that the subscript simply acts like a function replacement. If I want to work out a3, then we plug in and we get 2 times 3 to the 3 over 5 to the 3 plus 1, which in this case would be 2 times 27 over 5 to the 4th power, which is 625. So similarly, if I want to work out a sub n plus 1, I'm just going to replace all of these n's with n plus 1s. So I'm going to have 2 times 3 to the power of n plus 1 over 5 to the power of n plus 1 plus 1. So before I get to working on this limit right here, let me focus on this a sub n plus 1 over a sub n and see if I can simplify that a bit. We've just worked out that a sub n plus 1 is 2 times 3 to the n plus 1 over 5 to the n plus 2. And then I'm going to divide that by a sub n, which is 2 times 3 to the n over 5 to the n plus 1. Now to divide fractions means to multiply by reciprocals, so I'm going to have 2 times 3 to the n plus 1 divided by 5 to the n plus 2 times 5 to the n plus 1 over 2 times 3 to the n. This next step is probably the most important part here. There's lots and lots of things that cancel. To make it a little bit more clear, I'm just going to rearrange the numerators and the denominators. So I'm going to write the numerator has a 2 times a 3 to the n plus 1 and a 5 to the n plus 1. Just write reading across the top. If I read across the bottom, there's also a 2, there's a 3 to the n, and there's a 5 to the n plus 2. And so I can rewrite this fraction like this. I haven't done anything but reorder the way I'm multiplying things. But written like this, I can see lots of cancellations. 2 divided by 2 cancels. 3 to the n plus 1 over 3 to the n, well, we can subtract powers and find out that that simplifies to just 3. And 5 to the n plus 1 over 5 to the n plus 2, if we subtract powers, that simplifies to 1 over 5. So that means that a sub n plus 1 over a sub n simplifies to 3/5. That's what happens when the ratio test works. The fraction a sub n plus 1 over a sub n, which usually starts out terrifying, will hopefully simplify into something much nicer. In this case, 3/5. So let's pick up the story where we left off. We now need to compute the limit as n goes to infinity of 3/5. Well, I don't even really need an underlying function to tell you that that's exactly 3/5. And so we've worked out this limit. Now the ratio test says we have to take the absolute value of this limiting value r. So the absolute value of 3/5 is 3/5. And since that 3/5 is less than 1, that tells me that the series 2 to the 3n over 5 to the n plus 1 converges according to the ratio test. We knew that before, but it's nice to be able to repeat it. Now there's two things I sort of want to point out about this. First, like all of our other convergence tests, the ratio test does not say what the sum is. It only says, yes, there is a sum out there. Second, if that fraction a sub n plus 1 over a sub n ever simplifies to a constant, then the resulting series is actually a geometric series, and so we could use our Taylor ideas. Does the series n going from 1 to infinity of 3 times 7 to the n plus 3 over 2 to the 3n converge? If so, what to? Well, let's first see if we can answer the does it converge question first, because our convergence tests can do that fairly efficiently. Now, what test do I want to pick? Well, given that there's a lot of n's in exponents, that was a suggestion that the ratio test is a good call. So let's try to work out the ratio test, which involves taking the limit as n goes to infinity of a sub n plus 1 over a sub n. And then we call that limit r. So the first thing I got to do is figure out what this a sub n plus 1 over a sub n is. And that's just really a big algebra problem. We know what a sub n is because it's the series we're actually summing. It's 3 times 7 to the n plus 3 over 2 to the power 3n. A sub n plus 1 is the exact same series, but with all of the n's replaced by n plus 1's. So 3 times 7 to the n plus 1 plus 3 over 2 to the power 3 times n plus 1. Don't forget those parentheses, because you want to make sure that you group things correctly. So let's simplify this a bit. The numerator is 3 times 7 to the n plus 4 over 2 to the power of 3n plus 3, if we distribute through. To divide by the denominator means to multiply by its reciprocal, so we'll multiply by 2 to the 3n over 3 times 7 to the n plus 3. Now I'm going to do what I did last time. I know there's some cancellations to be had here. Let's just rearrange things to see the cancellations better. If I work across the numerator, there's a 3, a 7 to the n plus 4, and a 2 to the 3n. If I read across the bottom, there's a 2 to the 3n, which I'm going to group with this piece right here, a 3, which I'll group with the first term, and there's a 7 to the n plus 3, which I'll group with the middle term. And so we can write the original ratio like this. We haven't canceled anything, we've just rearranged the order that we've multiplied. So now we can get all kinds of cancellations out of this. 3 over 3 cancels and gets me 1. 7 to the n plus 4 over 7 to the n plus 3, we subtract powers, that gets me 7 to the first power. 2 to the 3n divided by 2 to the 3n plus 3, well, if we subtract powers, that would be 2 to the negative 3. And so, simplifying this, we have 7 over 2 cubed, or 7/8. And so that's my ratio. So now we can finish the ratio test, which says we're going to set r to be the limit as n goes to infinity of a sub n plus 1 over a sub n, or equivalently, the limit as n goes to infinity of 7/8. Well, obviously that limit is 7/8, and so we've taken care of r. Next, we have to do the absolute value of this. So the absolute value of r is the absolute value of 7/8, which is still 7/8. Since that value is less than 1, we can conclude by the ratio test that the series converges. So we've answered the first question. It converges. Now the ratio test doesn't say what it converges to, but we do have a hint in the work we've done. We saw that the ratio an plus 1 over an simplified to exactly 7/8, and so that's a clue that says that this series right up here is geometric. So let's actually see if we can work out what the series is, and see if we can find the geometric series function hidden in it. When n is equal to 1, we have 3 times 7 to the 4 over 2 cubed. When we have n equals 2, we have 3 times 7 to the 5 over 2 to the 6, 3 times 7 to the 6 over 2 to the 9, and then 3 times 7 to the 7, over 2 to the 12. And so that's my series. Now we know that a geometric series starts off with 1, so let me factor out this leading term, this 3 times 7 to the 4th over 2 cubed. When I factor that out, we're going to have a 1 plus 7 over 2 cubed, plus, when we factor it out again, we're going to have 7 squared over 2 to the 6, and then 7 to the 3 over 2 to the 9 on down the line. And actually, if we stare at that a little bit longer, that would be nothing more than, well, that's 7/8. This next term is 7/8 squared, and then 7/8 cubed, and then, check it out, there's that 7/8 right there. Since we know it sums, we can apply the Taylor series. We are inside the radius of convergence, and so we're going to have 3 times 7 to the 4 over 2 to the 8 times 1 over 1 minus blank, which in this case is 7/8. So that's going to get me 3 times 7 to the 4th over 2 to the 8th times 1 minus 7/8 would be 1/8. Since 1/8 is 2 to the negative 3, this simplifies to 3 times 7 to the 4th over 2 to the 5. And so there's the exact value of this series, without having to find a single partial sum. Does the series n going from 1 to infinity of 2 times 3 to the n over n plus 2 factorial converge? If so, what 2? Well, let's answer this first question. Does the series converge? If I take a look at it, it has 2 of the buzzwords that the ratio test is, well adapted to handle. It has an n and an exponent, an exponential piece, and it also has a factorial piece. So let's try to work out the ratio a sub n plus 1 over a sub n first, and then we'll try to take the limit of it. Now the a sub n piece we already know. It's just the terms we're actually adding up. 2 to the 3n over n plus 2 factorial. On the other hand, a sub n plus 1 is exactly the same thing, but with all of those n's replaced by n plus 1's. So 2 times 3 to the n plus 1 over n plus 1 plus 2 factorial. And now let's do our best to simplify this thing. So if I clean up the numerator, that's going to be 2 times 3 to the n plus 1 divided by n plus 3 factorial. To divide by the denominators, to multiply by its reciprocal, n plus 2 factorial over 2 to the 3n. Now, like I did in the other examples, I'm going to rearrange the numerators and denominators so I can so that I can line up the like terms. So in the numerator we have a 2, a 3 to the n plus 1, and an n plus 2 factorial. Reading across the denominators, we have an n plus 3 factorial, which will stick on the back end, a 2, which will stick on the front end, and a 3 to the n, which belongs with the guy in the middle. So I haven't done anything other than rearrange the terms. But now let's see if we get some cancellations. Well, once again, 2 over 2 cancels and gets me 1. 3 to the n plus 1 over 3 to the n, we can subtract powers, and that's going to get me 3. But what about n plus 2 factorial over n plus 3 factorial? Well, it turns out that a ratio of factorials always simplifies. It's kind of like trig of arctrig. But unfortunately, there's no magic triangle that you draw here. The best bet that I can give you is to write out several terms of this sequence and see if you can find a pattern. So for example, if we plugged in n equals 1, we would have 3 factorial over 4 factorial. When n is equal to 2, we would have 4 factorial over 5 factorial. When n is equal to 3, we would have 5 factorial over 6 factorial. But the first fraction is 321 over 4321. The 3's cancel, the 2's cancel, and all I'm left with is a fourth. The second fraction is 4321 divided by 54321. Everything but the 5 cancels, and we're left with a 1/5. The third sequence, everything cancels except for that lonely 6 at the bottom. So in other words, whenever we cancel factorials like this, all we're left with is the bottom number without that factorial. So n plus 2 factorial over n plus 3 factorial is going to simplify to 1 over n plus 3. It's just going to be that bottom number unchanged. So this expression simplifies to 3 over n plus 3. Since it's not a constant anymore, we know that this isn't a geometric series, but we've now simplified an plus 1 over an. Now what we have to do is take the limit as n goes to infinity of this expression in order to do the ratio test. This limit, remember, we're calling r. So now I have to take the limit of a sequence. Well, going back a couple sections, the first thing we do for sequences is change all of those n's to x's and ask if this thing is an underlying function. It is. And so we can now use our usual tools. If we plug in infinity, we get 3 over infinity, which is a 0. So we've just come up with r equals 0. The ratio test says take the absolute value of this. Well, the absolute value of 0 is still 0. 0 is less than 1. And so by the ratio test, we conclude that this series converges. So we've answered the first question. Does the series converge? But what does the series converge to? Now, our convergence tests never tell us that, right? The convergence tests simply answer yes or no. The only tricks we've seen for detecting what something converges to is to work out partial sums or to use the heredity principle. In this case, the series that we're looking at, if I work out several of the terms, we have 2 times 3 over 3 factorial, plus 2 times 3 squared over 4 factorial, plus 2 times 3 cubed over 5 factorial. These terms right here have both even and odd factorials in it, which might mean that it's a relative of e to the x. So let's see if we could bang that out here. Let's take e to the x, whose Taylor series has an infinite radius of convergence, so we can write it out as 1 over 1 factorial x, plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, plus dot 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 dot. And let's see if we can modify this sequence here, e to the x sequence, to look more like this one. Well, the one thing I notice in the sequence on the top is that it's got 3 being raised to powers. So let me replace all of these x's with 3's. So e cubed is 1 plus 3 over 1 factorial, plus 3 squared over 2 factorial, plus 3 cubed over 3 factorial, and then the next one would be 3 to the 4 over 4 factorial, which is looking pretty good. Of course, our original series started with 3 factorial. So let's just subtract these terms to the other side. So we're going to have e cubed minus 1 minus 3 minus 9 halves is equal to 3 cubed over 3 factorial plus 3 to the 4 over 4 factorial plus 3 to the 5 over 5 factorial on down the line. that's actually looking pretty good. This series here is now looking quite a bit like the series up top. The only difference is that there's an extra 2 in all of these terms, here, 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 which we could get by simply multiplying through by a 2. There's also a smaller power each time. The power's been gone down by 2, which we could do by dividing by 3 squared on each piece. So if we do that, we're going to have 2/9 times e cubed minus, I guess that's 4, minus 9/2. And on the right-hand side, we're going to have 2 times 3 over 3 factorial, 2 times 3 squared over 4 factorial, 2 times 3 cubed over 5 factorial. And that's the series we had from the beginning with. And if we distribute through here, we're going to have 2/9 e cubed minus 8/9 minus 1. And that thing simplifies to 2/9 e cubed minus 17/9. And so there's the exact value of this series. Once again, found out without doing a single partial sum. Does the series n equals 1 to infinity of 2n over n cubed converge? If so, to what? Well, once again, it seems as though we want to figure out whether or not the thing converges, and then we'll answer the question about what it converges to afterwards. Now we've got a bunch of tests for convergence, and once again I see the little buzzword here of 2 to the n. That's an exponential function, so I'm going to try the ratio test. So the first thing I'm going to do is work out this ratio of an plus 1 over an. Now what's an? That's 2 to the n over n cubed. An plus 1 is the same thing with the n's replaced by n plus 1's. So 2 to the n plus 1 over the quantity n plus 1 cubed. So if we flip this around, we're going to have 2 to the n plus 1 over n plus 1 cubed to divide by the denominators to multiply by its reciprocal n cubed over 2 to the n. So now if I regroup like I've been doing before, that's going to be 2 to the n plus 1 times n cubed in the numerator. And in the denominator, we've got an n plus 1 cubed, which I'm going to group with that second piece, and a 2 to the n. So now let's look for some simplifications. The 2 to the n plus 1 over 2 to the n simplifies and gets me just a 2. But what about this thing right here? If I tried to FOIL it out, I'm going to have an n cubed, and then n plus 1 cubed is n cubed plus 3n squared plus 3n plus 1, if you'd like. If you do this, then sit in shame in the corner for a while, because that's the deadly sin of false cancellation. In fact, nothing cancels here. There is no factor who's common to anything on the bottom. So in fact, the second term doesn't simplify at all. And the best we can do is get 2n cubed over n cubed plus 3n squared plus 3n plus 1. So sometimes it doesn't always simplify as much as you'd like. So now that I know what the ratio is, we can compute the r value, which is the limit as n goes to infinity of the ratio of an plus 1 over an. Or in this case, the limit as n goes to infinity of 2n cubed over n cubed plus 3n squared plus 3n plus 1. To work out this limit, we should check first if it has an underlying function. So I'm going to replace all of the n's by x's. So in the denominator, x cubed plus 3x squared plus 3x plus 1. In the numerator, 2x cubed. This is just a rational function. Rational functions have a finite number of discontinuities and a finite number of bends, so it's an underlying function. I can now use any calc tool I've got in my arsenal, and in this case, I'm going to use the leading term test, rather than L'Hopital's rule 3 times. So this is the same thing as the limit of 2x cubed over x cubed. The x cubes cancel, and that's the limit of 2, which is 2. So in this case, the r value is equal to 2. Since that value is larger than 1, we can conclude by the ratio test that this series diverges. So the series diverges, it doesn't converge to anything. These past several examples have sort of shown the general technique for evaluating the sum of an infinite series an. Essentially, it's a two-step process. The first step is to determine whether or not the series converges at all using a convergence test. And remember that we have a couple of basic tests. If it's easy to take a limit of the terms of the sequence, we can apply the divergence test to see quickly if it diverges. But the divergence test is frequently inconclusive. If the terms have an easily integrable underlying function, then the integral test gives us a perfect answer. Alternatively, if the terms look like the alternator minus 1 to the n times something with an underlying function, we've got the alternator test. And finally, if we've got a series that has factorials or powers, or we've just sort of run out of other ideas, we've got the ratio test. And these guys can detect whether or not the series converges. Once we know if the series converges, then it's worth trying to figure out what the sum is. The most effective way to figure out what the sum of a series is to apply the heredity principle and match it up to the Taylor series of a known function. You know you're going to be in the radius of convergence because you already checked that in the previous step. Of course, if you can't find a nearest relative or you can't quite make it match, that trick doesn't work. So you can always go back and look at the sequence of partial sums. Maybe you'll find a formula in the sequence of partial sums. More often than not, you won't, though. Nevertheless, 2 of our 4 tests, the integral test and the alternator test, came with error bounds so that you could gauge how accurate an approximation is. And that's in some sense the most you could possibly hope for. Does the power series, summation n going from 0 to infinity of 1 over 2 to the n plus 1 times x to the n, converge at x equals 1? How about at x equals 2? So let's answer each one of these questions separately here. Does the series converge at x equals 1? That means if I plug 1 into here, which would turn this into the series n going from 0 to infinity of 1 over 2 to the n plus 1 times 1 to the n, does that series of numbers converge? Well, if I simplify that up, that's the series n going from 0 to infinity of 1 over 2 to the n plus 1. And now I can ask the question, does the series converge? Well, what tools do we have in our toolkit that might help us out here? Let's look at the terms themselves. We have an is equal to 1 over 2n plus 1. Now, these terms clearly have an underlying function of 1 over 2x plus 1. It's a nice rational function, good to go. So we could attempt to apply the divergence test. We would take the limit as n goes to infinity of the terms 1 over 2n plus 1, which we could then swap out as the limit as x tends to infinity of the underlying function. As x goes to infinity, that gets me 1 over infinity, which is 0. Now, according to the divergence test, if the limit of the terms is equal to 0, the test is inconclusive. Alright, we didn't get any results out of that one. So let's try a different test. Because it has a nice underlying function, we could try the integral test. So the integral test would mean we would integrate the underlying function 2x plus 1, 1 over that, the x, evaluated from 0 to infinity. Since it's an improper integral, we're going to have to actually integrate it from 0 to a of 2x plus 1 to the negative 1 dx. And then we'll take the limit of that as a goes to infinity. So there's a quick little integration problem. So let's do the integration problem over here on the side. We've got the integral of 2x plus 1 to the negative 1 dx. That one's straight off the basic 20 as 1/2 ln of the absolute value of 2x plus 1 plus c. But we're not doing an indefinite integral, we're doing a definite integral. So we'll evaluate this from 0 to a, and we'll come up with 1/2 ln of 2 times a plus 1 minus 1/2 of ln of 0 times 1, or 0 plus 1. ln of 1 is just 0, and so that becomes 1/2 ln of 2a plus 1. So that's the expression that goes inside here. So now we need to go and take the limit as a goes to infinity of 1/2 ln of the absolute value of 2a plus 1. If we let a tend off to infinity, that's going to be 1/2 ln of infinity. We know that the ln curve grows without bound, and so this is going to be an infinity, which tells me that this series diverges. That the integral diverges. But since the integral diverges, the integral test says that the series diverges as well. And so, does this power series converge at x equals 1? No. What about at x equals -1/2? Well, the answer should be obviously no. Because if I think about this, we've got a Taylor series right here, which is clearly centered at 0. We know that if we tried to propagate the Taylor series out to 1, that it didn't work. -2 is even farther away from that, so we know that it cannot propagate out here. Our work has essentially showed that the radius of convergence of this series has to be less than or equal to 1. We can't get any farther than 1. But what if we hadn't done the first part of this problem, or we had selected -2 first? What could we do there? Well, if we plugged in -2 into this series, we would have the series summation n going from 0 to infinity of -2 to the n over 2n plus 1, which means that the terms are going to be -2 to the n over 2n plus 1. Now, this -2 bit right here suggests the alternator. So if we could rewrite the terms as -1 to the n times something else, that would work. Well, let's see. -2 to the n, that's the same thing as -1 times 2 to the n over 2 to the n plus 1. And then I can distribute this power through, because it's multiplication, and I come up with -1 to the n times 2 to the n over 2 to the n plus 1. So this series takes the form of an alternator times some other series. Now this other series, in the alternator test, that was the series we were calling Bn. If we have Bn equals 2 to the power of n over 2n plus 1, then we could write an underlying function, 2 to the x over 2x plus 1. The top is an exponential, the bottom is a linear function, has one discontinuity, no trig, so it's an underlying function. So the alternator test says we could take the limit as n goes to infinity of Bn. That would maybe be the same thing as the limit as x goes to infinity of 2 to the x over 2x plus 1, because it's an underlying function. If we plug in our infinities, we're going to get an infinity over an infinity on the top, which means we can hit it with the L'Hopital stick. If we do that, well, the derivative on the bottom is going to be 2. The derivative on the top is an exponential in disguise. We're going to get ln of 2 times 2 to the x by prepping and deprepping. We let x tend off to infinity again. We're going to get infinity on the top, 2 on the bottom. That's the value infinity, and that tells me we have divergence. So what does the alternator test say? Unless this series tends to 0, the series has to diverge. And so we've been able to answer the question, does it converge here? Also no. It diverges at both points. Of course, this alternator trick was kind of sneaky. I had to pull that -1 to the n out of it, and you might not have caught that on the first go-round. But that's why we have more than one convergence test. Looking at it again, I do notice that there's an n in the exponent, and that's one of the situations that the ratio test is apparently useful for. So we could try the ratio test. The ratio test would say we look at an plus 1 over an. Now an is the series that we were given, 2 to the n, -2 to the n, over 2n plus 2, or plus 1. Can't talk anymore. Up top, we're going to replace all of those n's with n plus 1s. So -2 to the n plus 1 over 2 times n plus 1 plus 1. Now I've got to simplify this fraction. So if I clean up the top, we have -2 to the n plus 1 divided by 2n plus 2 plus 1, or 2n plus 3. To divide by the denominator is to multiply by its reciprocal, which is n plus 1 over -2 to the n. Then we'll recollect the terms so we can see the cancellations better. Across the top, we have 2 to the n plus 1 times 2n plus 1. Along the bottom, we have 2n plus 3, which I'll group on the second piece, and -2 to the n, which I'll group on the first piece. So now we can ask if there's any cancellations to be had here. Well, in the first terms, -2n plus 1 over -2 to the n, we can subtract the exponents, and that's going to come out to being -2. On the second term, by gosh, do not do that. That would be the deadly sin of false cancellations. The top and bottom are as factored as they're going to get. They don't cancel at all. And so you're just going to have this expression right here. And so we've just shown that an plus 1 over an simplifies to -4n minus 2 over 2n plus 3. I'm just distributing the negative 2 through. So now I can work out this r value, the limit as n goes to infinity of this sequence. Well, once again, we can swap out all of the n's for x's. We'll get negative 4x minus 2 over 2x plus 3. This is clearly an underlying function, so I can apply the leading terms test. This becomes the limit as x tends to infinity of negative 4x over 2x. The x's cancel. 2 goes into 4 two times. And so that comes out with a value of negative 2. So r is equal to negative 2. Now we take a look at the absolute value of r. The absolute value of negative 2 is equal to 2. That's larger than 1. And so we can conclude for a third time that this series diverges. That might beg the question, where does this power series converge? Given the power series, what is its radius of convergence? How would we be able to work that out, given the tools we've got right here? Well, actually, it turns out that if you ever want to work out the radius of convergence, the ratio test is once again well adept at doing this. Let's see how the ratio test would work. So the ratio test, you take a look at an plus 1 over an. Now, our terms, in this case, I haven't substituted anything in, so our terms just look like x to the n over 2n plus 1. The a sub n plus 1 terms is going to be, now remember, replacing the n's by n plus 1. So it's x to the n plus 1 over 2 times n plus 1 plus 1. So if we simplify that, we're going to have x to the n plus 1 over 2n plus 2n plus 2 divided by, or multiplied by the reciprocal, 2n plus 1 over x to the n. So we regroup. We have x to the n plus 1 times 2n plus 1 on the top. On the bottom, we have a 2n plus 3 and an x to the n. So if we make the cancellations we can, the first terms cancel and leave me with just an x. The second terms don't cancel at all. And so we've got that an plus 1 over an is equal to x times 2n plus 1 over 2n plus 3. And now we want to take the limit as n goes to infinity of this. So far, nothing's changed from the last example, except instead of having, say, a negative 2 here, I've been just lugging around x, thinking of x right now as sort of being a fixed constant in this problem. In particular, it's not the variable in the limit, which is n going to infinity. So let's go and swap out our limit for an underlying function. Now, unfortunately, you can't do this. You can't change all of the x's, or all of the n's for x's, because the minute we do that, we've now confused ourselves between this x here, who was a constant in the problem, and this x here, who was the underlying function for a sequence. So just pick a different dummy variable right now. Instead of replacing the n's with x's, replace them with t's, which is sort of the second most common letter we use for variables. So the x doesn't change. The n's get replaced by t's. And so I have the limit as t tends to infinity of x times 2t plus 1 over 2t plus 3. Now, how do I want to take the limit of this thing that has two letters running around in it? Well, once again, remember that this x is a fixed constant, and constants can be pulled into the front of a limit. So I could write this as x times the limit as t goes to infinity of 2t plus 1 over 2t plus 3. Now, this could be done with any of the tools you want. If I take a look at, say, leading coefficient test, I will find that this expression right here is going to tend to 1. And so that gets me x times 1, or just x. So that's the r value. So that's the r value in the ratio test. So how does that help me? Well, let's do a little bit of work over here. We know that the r value is equal to x. That means, according to the ratio test, as long as the absolute value of r, which is the absolute value of x, is less than 1, then we have convergence. And if the r value of x, if the absolute value of r, which is the absolute value of x, is greater than 1, we have divergence. So put these two statements together, and it's clear that the radius of convergence is exactly 1. You converge if you are less than 1, you diverge if you are more than 1 unit away from the origin. And so we can actually work out the radius of convergence directly from this. You notice the one thing the ratio test can't tell us is the ratio test can't tell us what happens when r, or in this case the absolute value of x, is equal to 1, which happens at 2 points, x equals 1 and x equals negative 1. The ratio test can't tell me what happens on either one of these two guys. When x is equal to 1, we've actually seen that this series diverged. I'm going to leave it as an exercise to you to show that when x is equal to negative 1, the series actually converges at that endpoint. So the radius of convergence, we'd mentioned this before, that what happens at the endpoints is kind of arbitrary. It's sort of up to the power series. And in this case, one endpoint diverges and one endpoint converges. And like I say, try it on your own. Use the alternator test. This last example essentially shows us the basic procedure for finding the radius of convergence of a power series. The trick? Use the ratio test and treat x like a constant. In other words, find the value r, which is the limit as n goes to infinity, of an plus 1 times x minus c to the n plus 1 over an times x minus c to the n, using the usual thing, and then solve the equation absolute value of r less than 1. For whatever values of x work. If you don't quite remember how to solve an inequality, or you didn't learn that, the basic steps for solving an inequality is the first thing you do is you solve the equality. So set r equal to 1, which is the same thing as solving the equations r equals plus or minus 1. Those will give you critical points, and then you can use test values to work out the numbers in between. Remember that the radius of convergence doesn't say anything about what happens at the endpoints. So if you need to check whether or not the endpoints whether or not the power series will converge to the endpoints, you're going to have to do a separate check. Let's find the radius of convergence of the power series n equals 1 to infinity of 3n times 2 to the n times x minus 1 to the nth power. So, to find the radius of convergence, I'm going to attempt to use the ratio test. So that means I'm going to go and work out an plus 1 over an, simplify it and take a limit. Now an, the terms that we're playing around with, are 3n times x minus 1 to the n over 2 to the n. Then an plus 1 is the same thing with the n's replaced by n plus 1's. So 3 times n plus 1 times x minus 1 to the n plus 1 over 2 to the n plus 1. Notice I didn't make any changes right here because that's an x, not an n. Now we'll simplify and cancel as much as we can. So in the top we're going to have 3 times n plus 1 times x minus 1 to the n plus 1 over 2 to the n plus 1. I guess there's not much to simplify there. Then we're going to multiply by the reciprocal of that. So 3n x minus 1 to the n in the denominator, 2n in the top. And then I'm going to recollect my terms, which makes it easier for me to figure out what things I want to cancel. So across the numerator, 3, an n plus 1, an x minus 1 to the n plus 1, and a 2n. In the denominator, we've got a 2n plus 1, which I'll group with the last piece, a 3n, which I'll group with the first piece, and an x minus 1 to the n, which I'll group in the middle. So this is the exact same ratio, simplified. The 3's are going to cancel. The n plus 1 over n doesn't cancel at all. Any cancellations I make is the deadly sins. These are going to cancel and leave me with just an x minus 1, and these are going to cancel and leave me with just a 2 down below. So this will simplify to n plus 1 times x minus 1 over n times 2, or if you'd like, x minus 1 over 2 times n plus 1 over n, where I'm pulling these terms out in front because, for the time being at least, these are constants from n's point of view. Now I can go and find the r value, which is the limit as n goes to infinity of the ratio an plus 1 over an. That's going to be the limit as n goes to infinity of x minus 1 over 2 times n plus 1 over n. Now to work out this sequential limit, I'm going to use the underlying function principle and replace all of my n's with t's. So the first term doesn't change at all. The second term becomes t plus 1 over t. If we let t tend off to infinity using any tools you want, I know that this limit here will go to 1. So that means this limiting value is just x minus 1 over 2. So what do we find? Well, let's do a little bit of work over here. We found that r is equal to x minus 1 over 2. We need the absolute value of r to be less than 1. So to solve an inequality, the first thing you do is you solve the equality. I want x minus 1 over 2 in absolute values to equal 1. That means that x minus 1 over 2 has to be plus or minus 1. So that's just two small equations. X minus 1 over 2 is equal to 1, and x minus 1 over 2 is equal to minus 1. This first equation says that x minus 1 is equal to 2, so x is equal to 3. The second equation says that x minus 1 is equal to negative 2, so x is equal to negative 1. Let me get myself a little bit of extra space here. I'm going to move that arrow out of the way. There it goes. Now let me draw these things on a number line. On a number line, we've identified 2 points, negative 1 and 3. Let's test what values in this make the original inequality true. If I plugged in a test value of 0, the original inequality becomes 0 is less than 1. That works. So this stretch is okay. If we plug in a test value, say, 6 into the inequality, we're going to have 5 over 2, which is greater than 1, which means that this part is not okay, and similarly down here. So what have we shown? Well, let me summarize the work back over here. We've shown that the r value is less than 1 if x stays between minus 1 and 3. Notice that the number dead center of this interval, the number right in between minus 1 and 3, is exactly 1, which, not surprisingly, is the center of our series. And so we can move 2 units in either direction. And so we've just shown that the radius of convergence is exactly 2 on this example. So let's find the radius of convergence of the summation n going from 0 to infinity of minus 1 to the n over 2n factorial times x to the 2n. So, like last time, I'm going to attempt to apply the ratio test. So the first thing I have to do is work out the ratio of an plus 1 over an. Now, in the denominator, that's the power series, where I'm treating x now as a constant. So negative 1 to the n times x to the 2n over 2n factorial. And up top, I've got negative 1 to the n negative 1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial. I have to replace all of those n's with n plus 1's. So if we flip the fractions and clean them up, we're going to have negative 1 to the n plus 1, x to the 2n plus 2 over 2n plus 2 factorial. Flip the denominator, we're going to have 2n factorial over minus 1 to the n times x to the 2n. Now let's regroup all of those pieces. We have negative 1 to the n plus 1 times an x to the 2n plus 2 times a 2n factorial up top. Down below we have a 2n plus 2 factorial, which I'll group on the back end, a negative 1 to the n, which I'll group with the first piece, and an x to the 2n. Now I can hunt for cancellations. Now the first two terms cancel and leave me with just a negative 1. The second terms cancel, and by subtracting powers, I'm left with an x squared. Now the third terms don't cancel, but remember what I said before. A ratio of factorials always simplifies. The best way to figure out what it simplifies to is to just try some examples. So over here I'm going to do some scratch work real fast. If I plugged in 1, I'm going to get 2 factorial over 4 factorial. So that would be 2 times 1 over 4 times 3 times 2 times 1. And that's going to be 1 over 4 times 3. If I did 3 factorial over 5 factorial, that's going to be 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. The 3 2 1's cancel, and that's going to leave me with 5 over 4. If I did 4 factorial over 6 factorial, the same argument before, I'm going to have 1 over 6 times 5. So apparently, this expression always simplifies. It's always going to be whatever the number was in the bottom, and then the number that comes one less than it. So now let me use that argument and simplify this. It's always going to simplify to 1 over something. It's going to be whatever the number was in the bottom, 2n plus 2, times whatever number is 1 less than that. Well, 2n plus 2 take away 1 is 2n plus 1. And so when we've cleaned this thing up, we get negative x squared on the top over 2n plus 2 times 2n plus 1. And so now we've got the ratio of terms. We're ready to apply the ratio test. So we need to take the limit as n goes to infinity of negative x squared over 2n plus 2 times 2n plus 1. If we replace those n's with a new dummy variable, we're going to have t going to infinity, negative x squared over 2t plus 2 times 2t plus 1. Now keep in mind, if we let t go off to infinity, we're not going to get a negative infinity over an infinity because the top is a constant. That's why it's always helpful to pull that constant out before you attempt to apply any of your tricks. So I'm going to pull this constant out to the front, and we've got the limit as t goes to infinity of 1 over 2t plus 2 times 2t plus 1. Well, now this expression evidently goes to 1 over infinity, which is 0. And so we're going to get negative x squared times 0, which is just plain 0. So to find the radius of convergence, we have to go and solve the equation. 0, absolute value, is less than 1. But that means solving the equation 0 less than 1. And that's always true. It never changes. There's no value of x you could plug into there to make it ever false. And so we can conclude that the power series converges for all values of x. In other words, the radius of convergence is at infinity. And in hindsight, that shouldn't have been too hard to figure out, because we know that this is the Taylor series for cosine of x, if you write it out.